Okay, so periodic trends and transition metals, lecture 62. Name 3 trends of transition metals. So this is this block here, often called the D block, or transition metal block, or transition element block. That's where we have, for the most part, elements that have less than 10 D electrons, or can easily get rid of 1 or 2, so they have less than 10 or less than a full subshell of D electrons. So in that group, all of these metals have high melting points and boiling points, except for the 2B elements. One that you may be thinking of is so this would be in the far corner here, far edge. Mercury is one that we can think of that definitely doesn't have a high melting point. It's a liquid at room temperature, and that's due to its full set of D electrons, and simply doesn't even like to really interact with itself. So it tends to be kind of stay a liquid at room temperature and slightly below. Multiple oxidation states, that's true again for all of them. Iron is +2, it's also +3, sometimes these can even be +4, but cadmium, zinc, and silver have set oxidation numbers. That's all that they have. So when we talk about iron 2 and iron 3, we'd use those terms, but cadmium ion is just +2, zinc ion means +2, and silver ion means +1. Transition metal compounds often have a color to them, and they are, which we'll talk about later, and then they're usually paramagnetic. That is, they're affected by a magnetic field, which means they have unpaired electrons, and they're generally in the D sublevel. Okay. What are some exceptions to the building up principle in transition metals? Well, copper, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10, and chromium, 1s2, 2s2, 2p6, 3s2, 3p6. Looks like it should be 4s2, but it's 4s1, 3d5. When we fill up the, let me just make sure. So when we fill these up, according to the building up principle, this should be a 2 and a 2, this should be 9 and 4. But you can see that by putting that electron, one of them from the 4s over to the 3d, we completely fill this sublevel, which is very stable. If we do that for chromium, we half fill. So if we drew the orbital diagram, we have 4, it would be 4s2, 3d4 is what we'd expect by the building up principle, but if we remove one of these electrons, put it here, now we have 5 half-filled orbitals. Again, since they're all the same, there's a symmetry to it, there tends to be a stability when you have symmetrical systems. So this is very stable, so is a complete set of d orbitals. Describe how atomic radii change in transition metals. It wasn't by chance that we left off the way that the atomic radii increase and decrease when we talked about this in 1170. We only talked about the A group elements because they followed a nice trend. As you move down the group, they increased in size. As we moved over, though, they decreased in size. There was a decrease in atomic size when we were just dealing with the A groups. Well, what we find, there's a chart. I'm only going to do one example here. But we have, let me get it right here, we have niobium, tantalum, and then above that would be vanadium. So in this group, in the transition elements, you have vanadium, then niobium, then tantalum. And what we find is that the vanadium is smaller than niobium, as we'd expect, because vanadium has, let's get on the periodic table here, 23 electrons. Niobium has 41, and then tantalum has 73. Now, as you go from 23 to 41, almost doubling in size, yeah, we'd expect that vanadium is smaller than niobium. What we find, though, from niobium to tantalum, they're essentially the same size. So even though tantalum has 32 more electrons, it's pretty much the same size as niobium. So what's happening here is the same contraction that we see in the group A's. As we move across a row, we know that the atoms, lithium, which has 3 electrons, is actually larger than neon that has 10, because as we add in the electrons, they're all going into the same shell. They're all being affected in the same way by the nucleus, and so the only thing that's changing is the nuclear charge. Going from lithium, which is +3 to for its nucleus, to neon, which is +10. All of the electrons, they each have 2 core electrons. Lithium has 1 outer electron. Neon has 8. I'm doing a really bad job here. Let me just do this here. For lithium, neon has a +10 though, so lithium has a +3 charge at the center, 2 core electrons, and then this 1 outer electron being drawn by that +3. For neon, it has the 2 core electrons, and then it has 8 electrons outside, but they don't affect each other. They're all in the same level, so they all kind of ignore each other, but they're all drawn in by that +10. And what that does is it shrinks it, so shrinks the atom. So lithium, even though it has 7 fewer electrons, is larger than neon. So as we move across a row and we add in electrons into the same level, it actually decreases the size. Well, if we look at niobium to tantalum, if we follow the building up principle, we see that we go through the lanthanides. We have to add in 14 electrons that are used in finishing off the electron configurations of the lanthanides. So as we move across the lanthanides, lanthanum, cerium, praseodymium, neodymium, promethium, all the way across, these guys are actually getting smaller and smaller because we're putting electrons into the same level, but their nuclear charge is getting larger. So what happens is niobium, as we add in electrons past niobium, the atom gets larger, but then when we go to the next level down, we move through that entire row, through the S, through the F's, through the D's and P electrons, all the way across. We're reducing down the size so that when we come back around to tantalum, the size of the atoms have reduced so much that when we get to the next level up, the next row, tantalum, even though it's getting larger, it's only getting back to the original size. So, harder to draw here, but what's causing these guys to be the exact same size is called lanthanide contraction. And that's the answer. If you're asked why is it niobium and tantalum are the same size, lanthanide contraction. What's happening is that these electrons are being added into the same level, but the nuclear charge gets larger and larger, so the atoms get smaller. So by the time you go from niobium through back to tantalum, the atom has decreased so much in size that tantalum ends up being the same size as niobium, despite the difference in electrons. And that is that.